Bean. Bean. What are you doing? Stop. No. Spin.
I brought him, so I got him in January of 2020. And I brought him that semester, and then I haven't taught again until this semester, yeah. So he went for like 2 months and then this. Yeah, I'm thinking, so at home, I've trained him to stop barking at the door by, he like instead grabs a toy and then he'll just like take out his anger on the toy, like shake it really aggressively. So I'm like, maybe I should just bring one of those to class, and then instead of barking at people, he'll just like shake a toy at them.
Bumblebee. Oh, I'm skipping.
Okay, so let's go ahead and get started. So last time we talked about invertible maps. And today we're going to like use that to introduce this concept of isomorphism and when two vector spaces are isomorphic. And this is like, you remember like all the way back at the beginning when I gave like a spoiler about what happens, that today is like when we finally do the spoiler. Bean. No. You cannot do this. Okay, so isomorphism will tell us so whatever this is, this tells us when two vector spaces are the same. And this like concept appears like over and over again across like different areas of math. So like usually whenever you you introduce like any type of object that you're interested in, such as vector spaces, there will be like some idea of what it means for them to be isomorphic, and you consider them to be like the same when they're isomorphic. So so that's sort of like the intuition of this idea, is that like this will tell us when two vector spaces are the same. Okay, so let's go ahead and define this. So an isomorphism T from V to W is just an invertible linear map. So really, this is just like a different word for the same thing that we've been dealing with. And we say two vector spaces, V and W, are isomorphic if there exists an isomorphism T from V to W. Okay, so really this isn't like actually a new concept. We saw invertible linear maps last time, and recall that we also saw that a map was invertible if and only if it was injective and surjective. So that is what an isomorphism is. And I guess like, why do we say then that that V and W are like the same vector space? So the map T sort of just tells you how to relabel the elements in V to be elements of W. And other than that, like you really, other than just like the names of the elements and like the way that the vector space is presented to you, you really can't tell the difference between V and W. Are there questions? Okay, so now we'll do like a theorem, which is like sort of I think in my mind, this is like the main point of like linear algebra and why linear algebra is so nice. So the theorem says that two finite dimensional vector spaces over some field F are isomorphic if and only if they have the same dimension. Okay, so like, why is this a big deal? So like, for example, if you continue on to abstract algebra next semester, we'll introduce something called a group, which is like just another type of algebraic object. And in groups, you also have an idea of when two groups are isomorphic, but we are like nowhere close to having a classification for finite groups. So like, that's like an open area of like active research. So there's like lots of people working on like classifying finite groups. But in the case of vector spaces, you do have this classification. Like when the vector space is finite dimensional, then you know that like the only piece of data that you need to know what vector space it is the field F that it's over and its dimension. So this theorem really tells you that like vector spaces, we really know everything that's going on for vector spaces. Are there questions about the statement of the theorem? Okay, so let's go ahead and prove it. So this is an if and only if statement, so we have to prove both directions. So let's start by doing the forwards direction. So we'll suppose that V and W are finite dimensional vector spaces, and that they are isomorphic. Then what we want to do is to show that dim V is equal to dim W. And I'll give you a few minutes to think about how to do this. And my hint is to use the rank nullity theorem. So go ahead and take a few minutes to think about how to prove this direction and discuss with each other. And then we'll do the proof together at the board. You're a bad
You know that there's the other one next, I have to prove that there's a next one. Yes. Which means I have to prove that the answer. Okay. Yes. So you know that there has to be an index here. Because it's less
Okay, so let's go ahead and prove this direction. So the hint was to use the rank nullity theorem. So let's suppose that T from V to W is an isomorphism. Okay, then by the rank nullity theorem, we can just write dim V is equal to dim null T plus dim range T. And then what do we know about dim null T and dim range T? Yeah.
Dim null T is 0 because it's injected, which means that it's the 0 value, and then range T since it's surjected is W, so it's dim W.
Yeah, so dim null T, we know that this is 0 since T is injective, and then the range of T is all of W since T is surjective, so this will be equal to dim W. So to summarize, this just says that dim V is equal to dim W.
Does that mean she has to be
Sorry, can you say your question again?
Does dim of the range of T have to be exactly equal to dim W? Can't be greater than
So range T is a subspace of W, but also the range is all of W since it's surjective. Yeah, so the dimensions will be the same. Okay, so that finishes this half of the proof. Are there questions about this? Okay, so then for the other half, so for this part, we would suppose V and W have the same dimension. And then we want to show that they're isomorphic. So how might we do this? Yeah. Yeah, so let's create, so the idea is to create a linear map T from V to W, which is an isomorphism. So, i.e., it's invertible or injective and surjective. So how might we create such a map? Yeah. Yeah, so let's fix V1 up to Vn, where n is the dimension of the two vector spaces. So let's let this be a basis for V, and W1 up to Wn be a basis for W. Then we'll define T from V to W by the following. So we'll just ask that T send the ith basis vector of V to the ith basis vector of W. So it just sends one basis vector to the other. And then we had a result previously that told us that this does in fact define a linear map. So now we have to show that this is an isomorphism. So how might we do that? Yeah, someone.
You could show that it's injective, you say kind of reasoning that.
Yeah. So we can just show that it's injective and surjective. And it's injective because so if something maps to 0, then that means that we have a linear combination of the W's that equals 0. But since the W's are a basis, they're linearly independent. So that means that in fact, the thing that we mapped to 0 must have been 0. So null of T is equal to 0. Since maybe I should write more because I just said a bunch of stuff. So since if T of some vector V is equal to 0, we have whatever T of V maps to, it's some linear combination of the W's. And that implies that the A sub i's are all equal to 0. Where, let's say, so the A sub i's are those coefficients that write V in terms of this basis. Does that make sense? I feel like I went through it a little bit quickly. Okay, so why is T surjective? Yeah.
Already proved that injective nullity is equal to 0. If you use the right nullity, you can just say div B equals 0 plus div range T, then range T is equal to.
Yeah, okay, so since dim, I need more room. Since dim null T is equal to 0, we have dim V equals dim range T, but also this is equal to dim W. So W is equal to the range of T. Beam, there's nothing in there for you. Yeah.
The same, for this last step, you said that the 2 dimensions are the same, so therefore the sets are the same. Doesn't that rely on what we're doing right now? Or
so we already know that range T is a subspace of W. So if it has that that maximum dimension, then it has to be, yeah, equal. Other questions? Yeah.
Just clarifying why these
Yeah. So going back to like here, so I can write any element of the vector space V as a linear combination of this like basis. So if I apply T to such a thing, then I get a linear combination of the W's with those same coefficients that equals 0. But since the W's are a basis, they're linearly independent. So that means that all of it, A sub i's had to be 0.
Okay.
Yeah. So then, in fact, like this whole expression must have been 0.
Okay.
Yeah.
Okay, so that makes sense. Okay. There's no other way you can get 0.
Yeah. Mhm. Other questions? Okay, so then the corollary of this theorem is like the thing that I told you at the very beginning of the semester. So if V be a finite dimensional vector space over F, then V is isomorphic to F to the N for some N. So we've seen like a lot of these like weird vector spaces, like vector spaces of linear maps, or that one weird vector space from the problem sets. So it turns out that they are all secretly in some way just F to the N for some N. And we'll see an example in a second. Are there questions about like, I have to go all the way back to the theorem statement. Oh no, it's too small now. Okay, are there questions about this, the theorem or the corollary or the proof or anything before we see an example? Yeah. Wait, can you say it again louder?
Yeah, so for range T, is something we probably would use that. We know it's equal and the range is less because.
Yeah, so we know, so we have that T, range T is a subspace of W, and we also have that the dimension of range T is equal to the dimension of W because of rank nullity.
So because.
Yeah. Yeah.
Corollary is that V is dimension F.
Yeah. Yeah, I guess instead of for some N, I could just say where N is equal to the dimension of V. It's like more precise. Okay, so let's do an example. So recall the vector space. So let's let V be an n-dimensional vector space. And W be an m-dimensional vector space. And just recall for a second the vector space LVW. So what was this? This was the space of linear maps. Do you guys remember this? So we put all of the linear maps from V to W together form a vector space. Yeah. The field is going to be the same as whatever the fields for V and F are, or sorry, V and W. So these have to be the same. V and W have to be vector spaces over the same field, and then the vector space of linear maps will be over that field as well.
So why did you already speak that earlier that you have to be over the same field?
Yeah, so for example, like, homogeneity like doesn't make sense unless V and W are over the same field. Like, how would you do like T of lambda V, lambda T V, like I only know how to do the multiplication in both situations if V and W are the same vector space.
I think it was-
Or so, or over the same field.
I think it was shown like the input data, especially show that like you can make it that and then later and have between like the even numbers and like I think there's an even number and then like negative integers.
So that was a bijection, but it's not a linear map. Yeah. Okay, so we have this vector space of linear maps from V to W. So then, by this corollary, it's isomorphic to some F to the N. And what should it mean? Okay, so the vector space LVW of linear maps from V to W is isomorphic to F to the something. And what should the something be? Yeah. Yeah, so this should be the dimension of LVW. So what is that in terms of the dimension N and M? Yeah. So. And F to the M times N, so this we can view as the space of M by N matrices, right? So we're gonna, so just to like summarize, we're gonna prove that the vector space of linear maps from V to W is isomorphic to the space of M by N matrices. Can anyone think of what the isomorphism might be? Yeah.
You have like a matrix of n by n elements, and you can just kind of like lots of one of n times n elements.
Okay, yeah, so I'm thinking of, yes, so I'm thinking of like F to the M times N as like, so that's like one really long vector. So this is isomorphic to the space of M by N matrices. And I'll just like draw a picture. So if I had like one really, really long vector, then I would just rewrite this as like a matrix filled with, we can make a better picture. So that would be like the first n elements, and then the next n elements, and so on. And there would be m total of these. Okay, so that's why Fmn is isomorphic to Fm times n, the space of m by n matrices. So So to prove this proposition, we need to find an isomorphism from LVW to FM by N. Yeah. Yeah, so the idea is to use this the matrix thing. So we know if we have a linear map T in LVW, we know how to associate a matrix for that linear map called M of T. So we want to show, so the idea is that like maybe this isomorphism is that map M. So is M from LVW to FM by N a linear map? Or I guess we want to show more than that it's a linear map. We want to show that this is an isomorphism. Yeah.
Is you want to show that given a particular map, you can make a matrix of it, and you can help to make a map.
Yeah. Yeah. So we already have shown like a while ago that this was a linear map, but we didn't say it in those words. So we already proved that or like basically we defined the matrix operations so that this would be true. So M of T plus S is equal to M of T plus M of S. And we also had M of lambda T is equal to lambda M of T. So together, those two equalities tell us that M is a linear map. And now to show that it's an isomorphism, we could just show that it's injective and surjective. I'm going to give you a few minutes to think about why the map M is injective and surjective, and then we can talk about it after. Okay, so let's go ahead and prove this. So I guess I feel like maybe I might have lost you all a little bit in like this part. So are there any like questions you have that I can clarify about this setup? Yeah. Yeah, so this is the space of m by n matrices. Over the field F. Yeah. Other questions? And yeah, and then the other thing is like, of course, in order to make a matrix of a linear map, we first need to fix bases of V and W. So I'll just go ahead and fix some bases. Okay, so how do we show that M is injective? So I guess we can do just the way that we show that anything is injective. So let's just suppose for some T, some linear maps T and S. So suppose for T and S in LVW, we have M of T is equal to M of S. And then we want to show that T and S or I guess that T is equal to S, so that those are the same linear map actually. I'm just gonna move that down. Okay, so since we know that these two matrices, M of T and M of S, since we know that those are the same, we have a way to say what these linear maps do to a basis, right? So so our basis for V is called the V sub i's. So T of V sub I, this is equal to, we're looking at that ith column of M of T, right? So this is the sum as J goes from 1 to M, which is the dimension of W. M of T sub J comma I, W sub J. Okay, so recall that, like, what does this matrix consist of? The columns tell you what T of VI is. Okay, so we have this. But we know also that M of T is equal to M of S. So this is equal to, I'm just going to replace M of T by M of S because they're equal. So this becomes M of S sub Ji Wj. Okay. And then looking at that line, that's just thinking of the definition of the matrix of the map S. This is actually equal to S of V sub I as well. Okay, so we know that T and S are two linear maps that do the same thing to every basis vector. So therefore they must be the same map. So T is equal to S since T of VI is equal to T of SI for I from 1 up to N. Yeah. Okay, does that make sense? Yeah.
You can also on the first step, subtracting M of S and then M of T and minus S equals 0, since they both keep the same size. And the V sub I, the M of S and the matrix is the same.
Yeah. Yeah. Okay, so I know this is like tricky because we've gone like we've like added a layer of abstraction to what's going on here, right? Because we're making a map of the space of linear maps. So I know it's like confusing, but hopefully, you know, we're just going through this routine now of showing that something is injective by just saying, you know, if it maps two things to the same thing, then we want to show that those two things are equal and just like go through the motions and we get to the proof. Okay, so for surjective, how do we show that M is surjective? So we have to show that if we have something in the target, then I can produce something in the domain that maps to that. So we'll just let A be any M by N matrix over F. So we want to produce some T from V to W such that M of T is equal to A. Okay, and then that will have shown that M is surjective. So let's define T to be the linear map where T sends the ith basis vector to the following. So what we want this to be is we want A to be the matrix of T. So that means that the columns of A tell us where the basis vectors VI should be mapped to. So this is going to be the sum as J goes from 1 to M of A sub J I W J. Okay, for any I from 1 up to N. Then, by the way we've defined this, the matrix of T will equal exactly that matrix A. And so M is surjective. And that finishes the proof. Are there questions about this? Yeah, so basically, like, if I were to write down what is M of T, the coefficients in M of T would be exactly these A, J, I, right? Just because of the way we define T. So then we would have M of T equals M of A. Yeah, yeah. Oh yeah, so we have this result that says, like, if I tell a linear map, like if I can define a linear map just by what it does to a basis, and that makes a linear map, and it's the unique one that does that and all of that. Yeah. Okay, so that's it for today. If you want to think about this in like a concrete example, you might think about, for like a couple of problem sets ago, you had a problem that asked you to find all of the linear maps from R2 to R2, or a basis for that space. So now you can think about that problem in the context of this proposition, and hopefully that will like make sense and clarify all of this. And I'll see you on Friday. Yeah.
One more question before, so I mean, this is the proof on the package.
Yeah.
But I don't understand how these steps are connected, because in the book, so they define like I mean equals.
Yeah, so they use kind of a different notation.
Yeah, but I mean, they are different, right? But the book just states that because of this, so we can connect these two steps. So try to understand.
I don't know. So is this the definition of that notation?
Yeah. This 3.64 on textbook, and also it's just say that based on 3.64 we can get it, but I don't understand.
Yeah, okay. I don't really understand this notation.
I think this means that the first row, this means the first row of the matrix of T, and this is the nth row, column. The first column and the nth column of the matrix of T. Yeah.
Okay. Okay, then that makes sense, because this is, so what is M of TV? It's like you write V in T of V in terms of the basis of W. So that's just going to be the ith column of T, of the matrix of T.
So I mean, this is the linear map of a vector in the basis of V, right? So this is part of the basis, and then I got the column.
Yeah, so this is M of T V1. So this is like a column that tells you how do you write T of V1 in terms of the basis vectors of W. And that's exactly what the ith column of M of T does.
Okay, I understand.
I have a much simpler question.
Uh-huh.
I just was confused. So for that, we concluded that T equals X since T VI equals X VI. But what if you had like two different maps that just happen to map like one particular thing to the same place? Like how, then it wouldn't be objective, right? Like if you had two separate linear maps that
Wait, say it again. So if you had on which part?
for here, like if you had two separate linear maps that mapped one particular
Oh, yeah, but
vector
they,
to the same spot, like how can we
so
conclude?
they do this for every basis vector.
So for every v sub I,
Yeah, and there was a result in the book, which is numbered 3.5, and it says that so if you define a linear map by like what does it do to each basis vector?
Okay.
Or if you define a map by doing that, then it is a linear map and it's unique.
Uh,
So the fact that we know that like that these do the same thing to each basis vector, that actually already tells you that those are the same linear map. Yeah.
okay,
I didn't see the notes for last week.